In the presentation that accompanies this video, it asks the question, what is the preferred method of sizing weld flaws using phased array inspection? With the two examples from the presentation, we're going to demonstrate both amplitude drop sizing and shear wave tip diffraction and explain under which conditions each is most beneficial. The first flaw detected in the C-scan is a high amplitude linear indication, and based on its S-scan and A-scan characterization and its location within the weld, with certainty it can be determined as lack of fusion. Length sizing for the lack of fusion indication is best performed on the C-scan. The lack of fusion is near perpendicular to the orientation of the beam, and it is a large linear indication that is larger than the beam, indicating an amplitude drop sizing technique using the color palette and A-scan amplitude will return best results. The length sizing is determined on the C-scan based on the color palette representing amplitude for a 6 or 3 dB drop or a rapid drop sizing technique. In this case, we are using the color palette to visualize a 6 dB drop for a total length size of 29 millimeters. Within the length of the flaw on the scan axis, we want to identify the depth and the height of the flaw. The height of the flaw in the presentation was measured at a scan axis position of 43 millimeters at an angle of 64.5. This represents the 6 dB drop on the top of the fusion. We'll put one cursor at that position. And we can tell that the flaw is connected to the ID, or the inner diameter of the pipe, by looking at B0, and we'll put another cursor directly at the depth of the pipe for a through wall dimension of 5 millimeters in height. The depth is coming from the gate data in gate A for this A scan at 19.99 millimeters. We've identified the length, depth, height, and we will add that indication to the report and move on to the next example. In this example, we have a thermal fatigue crack detected in the volume of the weld on the second skip. We can tell by lack of a corner trap on the end of the second skip that it's not connected to the pipe OD surface. Length sizing, regardless of flaw type, is determined on the C and B scan using, in this case, a rapid drop technique, because as the flaw changes depth, height, and orientation, it has no relationship to the maximum amplitude determined as we mark the extremities of the flaw. We'll place one cursor at the extremity on one side. In this case, it was detected differently by both probes, and we're going to use the group 2 to identify the start of the crack, and we'll use group 1 to identify the stop position of the crack for an overall length of 50 millimeters. In the presentation, the top of the flaw was detected at 706 on the scan axis, and we can see we have varying tip diffracted signals showing the different ligaments of the crack. We're going to identify the deepest of those and place one of our two cursors directly on the center of the energy for a tip diffracted technique. These ligaments are smaller than the beam, so no color palette is going to be used to try to do a dB drop technique to identify the extremities. We're going to identify the tip center energy based on the color palette of the signal. So we've identified the deepest or the bottom of the crack, and we will now identify the top of the crack. In the presentation, that occurred at 689. And if I bring my data cursor down, here's the tip diffracted signal. It's not connected to the outside surface. I can see the crack geometry as I move the A scan through the S scan. I'm going to identify the center of the deepest tip with the second measure cursor. For a through-wall dimension of 10.78 millimeters from crack bottom to crack top, and a length of 50 millimeters. As I move the data cursor through the crack on the scan axis, I want to be sure that no tip occurs shallower or deeper. We'll record it on the deepest tip. Add this indication to the database. And again, shear wave tip diffraction, most beneficial on crack type indication where the ligaments are smaller than the beam size. Amplitude drop where there is favorable orientation. Near perpendicular, typical of weld bevel flaws such as lack of fusion.